Okay, last experiment. This is the Prelab video for calorimetry. Almost done. All right, before we get started, well, I guess this is part of the start. I want to introduce you to a really simple equation that basically explains energy and temperature and the relationship of those two as it goes into changing the temperature of a substance, all right, or a body of some sort. So we have this little symbol here, little Q, and this represents heat. Heat is in the form of energy, and it's in units of joules typically. It will be in units of joules for this experiment. And energy, heat, equals the mass of a substance times the specific heat of a substance times the temperature change of that substance. Okay. Mass is self-explanatory. Specific heat, that is a characteristic that is associated with the substance. Not all things have the same specific heat. Water has a specific heat of 4.184 joules per gram per degree Celsius. And we'll be using that a lot in this experiment. So that is specific to the substance, specific heat. Right? Ethanol, for example, will have a lower specific heat than water. Right? So it's a very simple calculation, and this is the backbone of calculations we're going to be using in this experiment. Let's use this calculation real quick. So let's say that we have water. We have some water, and the mass of the water is 50.0 grams. All right, so we have some water, 50 grams, 50.0 grams of water. And we know the specific heat of water. I'll just call C sub W. All right, specific heat of water. That is 4.184 joules per gram per degree Celsius. Those are the units. Let's say the water starts out at 25 degrees Celsius, 25.0 degrees Celsius, and it warms to 50 degrees Celsius. All right, so we're warming water up to 50 degrees Celsius from 25. So we're adding heat. We're adding heat to the water, adding energy to warm the water up to 50 degrees Celsius. All right. So the initial temperature of water, T sub I. T sub I, initial temperature of water, we said it was 25.0 degrees Celsius. And the final temperature of water, when we're done heating it, is 50.0 degrees Celsius. All right, so these are our conditions, and we want to know how much heat it took to heat 50 grams of water from 25 to 50 degrees Celsius, and we use this calculation. All right, so Q is going to equal the mass of the water, 50 grams, 50.0 grams, times the specific heat of water, right there it is, 4.184 joules per gram per degree Celsius. All right, delta T. Now this is very important, so pay attention. Delta T is determined, calculated by taking the final temperature and subtracting the initial temperature. Right? Final minus initial. It's always done that way. You got to keep your bookkeeping straight. I'll discuss that a little bit later. So the final temperature was 50 degrees. And the initial temperature was 25.0 degrees Celsius. All right. So there's our calculation. Now the units cancel, grams will cancel, and Celsius would cancel out here. and what we're left with is joules. That's what we want. I'll do that calculation real quick. Okay, we're limited to 3 significant figures here. So this would be 25.0. Yeah, 3 significant figures. So I get 5,230 joules. Okay, so it takes 5,230 joules to warm 50 grams of water from 25 degrees to 50 degrees. Pretty simple. Okay, let's do a little experiment here. So let's say we have this container. There's the walls of our container, like so. And let's say in this container we have 50 grams of water. Up here, 50.0 grams of water. And it's at 25 degrees Celsius. Okay. And to this water that's at 25 degrees Celsius, we're going to add 50 grams of water that's at 75 degrees Celsius. Okay. Now, obviously, when we mix these two samples of water, it's going to all mix together. It's not going to form a little line here, but we can do this as a thought experiment. Right? We can imagine that this water is separated and that the temperature gradient here is going to change over time, right? So the cold water is going to warm up while the hot water cools down. And they're going to meet in the middle. Right? Rationally speaking, they're going to meet in the middle. Whatever energy leaves the hot water and goes into cold water has to be the same amount of energy that enters the cold water. Now this is just called the first law of thermodynamics. So up here, let's describe this process using this equation. Okay? This equation right here. So how much energy goes into the cold water? Q sub C. We're going to call it Q sub C for the cold water. That's going to equal the mass of the cold water. Mass of the cold water. Specific heat of the cold water. And delta T of the cold water. And the heat down here, associated with this sample of water cooling, it's going to be the mass of the hot water, specific heat of the hot water, which is the same as the cold water, and the delta T of the hot water. Okay. Now here's the thing. Q sub C, well, Q overall, well, Q sub C plus Q sub H, right? The heat process associated with the cold water and the heat process associated with the hot water must equal 0. Must equal 0. That's the first law of thermodynamics right here. All the heat processes must sum to 0. Energy can't be created or destroyed in this universe. It is constant, as far as we know. So all the heat processes must equal 0. So let's take this equation here and write it in these terms. So Q sub C is just that term. M sub C delta T. Okay. So that's what this is, according to that equation, plus now Q sub H all this must equal 0. So we plug all these values in. So 50 grams of cold water, and I'm just going to drop units for now. Right, delta T for the cold water. Well, the final temperature of the cold water, remember, start at 75 degrees here and the 25 degrees for the cold water, and they're going to meet in the middle, which means they'll meet at 50 degrees. This one's going to cool 25 degrees. This one's going to warm 25 degrees. So the final temperature is going to be 50 degrees. Final temperature is going to be 50 degrees. The final temperature of the cold water will be 50. The final temperature of the hot water will be 50. So the final temperature of the cold water is 50.0 minus the initial temperature was 25 degrees plus mass of the hot water specific heat of the hot water. Well, it's water, so it's going to be the same, 4.184. Final temperature. The final temperature of the hot water is 50. And the initial temperature was 75. And all this must equal 0. Okay, so here's what I'm talking about over here. This is going to be a negative term. 50 minus 75 will be minus 25.0. That's going to make this entire term negative. As a matter of fact, I already did this calculation up here. All right. You can see that these are exactly the same numbers as this down here. So this will turn out to be 5,230 joules. This term over here will be minus 5,230 joules. And lo and behold, it equals 0. Now, of course, we defined everything to be that way. But I'll write this. This would have been a negative 5,230 joules. This is minus 5,230 joules. Okay. Now, what does this negative sign represent? That represents energy leaving the system, or energy leaving the substance. So in the hot water case, energy left and went to the cold water. And that's why the cold water warmed. A positive value for heat tells you that energy is going into the substance. Right? So the cold water received 5,230 joules, and the hot water lost 5,230 joules. So plus a negative is just a negative, just a minus. So we can write it like this. Okay. So let's say you did this experiment. You did this experiment right here. It turns out you wouldn't get this. You wouldn't get this result. Wouldn't get the result. As a matter of fact, the hot water would cool a little more than the cold water would warm. Right? So it's like more energy left the hot water than went into the cold water. Now, why is that? The reason is that we have these walls of the container, and they are also going to absorb heat. So not all of the heat goes from the hot water to the cold water. Some of it goes into the wall of our container. And we're going to call this container the calorimeter. And we have to take into account for that. So we actually have to write this term. We have to give it another term, actually. It's not so simple, but it's not that much more complex. So we can write it heat of the cold water, heat processes of the hot water, heat process of the cold, heat process of the hot water, plus the heat process associated with the calorimeter. Calorimeter. That's what we're going to call this container here. That's our calorimeter. Now this, we've taken into account all the heat processes. This must equal 0, and it will. Okay. So we can expand this term now. So this would be really M sub C, specific heat sub C, delta T sub C, plus M sub H and now we have to write a term for the calorimeter. It's the mass of the calorimeter, specific heat of the calorimeter, and delta T of the calorimeter. All that must equal 0. And here's a key point. This is what you're going to do the first part of the experiment. I'm actually the one doing it, but this is what you're going to calculate. You're actually going to calculate the specific heat of the calorimeter. We need to calculate this for the other two steps in the experiment. We need to know what the specific heat of our calorimeter is. Our calorimeter is just 2 styrofoam cups, sleeved together with a lid. But we need that value. Once we have that value, then we can use our calorimeter to do some experiments, and that's what we're going to do. So the first experiment I'm going to show you, you're going to have all these values. Right? You're going to have the mass of the cold water, specific heat of the cold water. That's just the specific heat of water. It's 4.184 joules per gram per degree Celsius. You'll have the temperature change of the cold water. You have the mass of the hot water, specific heat of the hot water. It's the same as the cold water. Delta T of the hot water. You'll have the mass of the calorimeter. You'll have delta T of the calorimeter. All that's the data that you're going to be able to gather when I show you the experiment. So you'll have this entire term, you'll have mass of the calorimeter and delta T of the calorimeter. And all you have to do is find this. Just use some algebra to find that value. Specific heat of the calorimeter. That's the first part of the experiment. I want to go ahead and tell you right now, though, that in the experiment, what we will do first, what I will do is I'll add some water to the calorimeter, and you'll take the mass difference. You'll have the mass of the calorimeter, then you'll have the mass of the calorimeter plus the water. Take the difference there to get the mass of the cold water. Right? And the cold water, so-called cold water, will sit in the calorimeter for a period of time, and it'll equilibrate. So the initial temperature of the cold water will be the same as the initial temperature of the calorimeter, because they'll be in thermal contact, they'll be at the same temperature. Now, after that, I'm going to warm some hot water, and I'll pour the hot water into the cold water that's in the calorimeter, and we'll follow the temperature change. Temperature will start out low, and it will rise. Now, the final temperature will be the same for all these. Right? Final temperature of the cold water, the final temperature of the hot water, and the final temperature of the calorimeter be the same value. That's when everything is in first thermodynamic equilibrium. And that value is obtained by taking the highest temperature reading. Right, so you have a thermometer stuck over here in this calorimeter, the cold water. I'll pour the hot water in. We'll use that thermometer to follow the temperature change. And it'll go from whatever value, around room temperature, 21 degrees or so, up to maybe it'll go to 30 degrees. And then it'll stop. That'll be the highest temperature. That will be the final temperature. And that's the final temperature for each one of these. Okay? So, with what I just said, you should be able to understand that delta T of the cold water is going to equal delta T of the calorimeter. Right? The initial temperatures are the same, and the final temperatures are the same. Okay. That's the first experiment. Second experiment. Second experiment, we're going to have a calorimeter, and it's going to have some water in it. And This water will be at room temperature, it'll be a lower temperature, and I'm going to place a hot metal block into the calorimeter. Okay, so this is the metal block. Our water will be up here. Okay, so this metal block is going to be much hotter than the water. And so heat is going to leave the metal block. And it's going to go out. Some of it will go into the walls of the calorimeter, but it's going to go, a lot of it's going to go out into the water to warm the water. Okay. So in this case, we're going to have the heat process associated with the water, the heat process associated with the metal block, that's sub M, and the heat process associated with the calorimeter. All that must equal 0. Well, we know what this is. It's the mass of the water, specific heat of water, delta T of water, plus the mass of the metal block, specific heat of the metal block, delta T of the metal block, plus the mass of the calorimeter, specific heat of the calorimeter, delta T of the calorimeter. All that must equal 0. So in this experiment, we are trying to find the specific heat of the metal. Okay. So from the experiment, you will have all this data. You'll have all this data. We know this because we determined that in the first step of the experiment. You'll have the mass of the metal, and you'll have the temperature change of the metal. Okay. So you have all these values, solve algebraically, and determine the specific heat of the metal block. That's the second experiment. All right, third experiment. Third experiment. Again, we have a calorimeter. And we're going to pour into this calorimeter, we're going to pour 1 molar, about 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide. So it's an acid-base reaction. And reactions either consume heat or they give off heat. They either take in energy from their surroundings or they give off energy into the surroundings. So a reaction will occur in here. This is what I'm representing as a reaction. RXN, reaction, RXN. Okay. Now think about this. Hydrochloric acid solution, it's 1 molar. It's a solution. It's an aqueous solution. Most of that material is water. Most of it's water. Same thing goes for the sodium hydroxide solution. Most of it is water. Most of it is water. So this reaction is basically taking place in a water environment. The water is surrounding it. The reaction is taking place. It's either taking in energy from the water or giving off energy into the water. So in this process, we have Q associated with the water, specific heat of the water, delta T of the water, okay, plus heat of the reaction, QRXN. What we're trying to determine is the enthalpy of this reaction. What is the enthalpy of this acid-base reaction between hydrochloric acid and sodium hydroxide? QRXN. This is the value that we're trying to determine. All right. It doesn't have a MC delta T associated with it. This is the term itself we're trying to find. And then we have our mass of the water. Sorry about that. Mass of the water, QRXN, Then over here we have the mass of the calorimeter. Specific heat of the calorimeter, and delta T calorimeter. All that must equal 0. So from this experiment, we'll have all this data and all this data, and then you just solve algebraically for enthalpy of reaction. That's basically it. I'm going to tell you right now that this metal that we're going to use is aluminum. And you're going to calculate the specific heat experimentally for aluminum. But I want you to compare that value that we get experimentally to an accepted value. Right? You can find an accepted value just using Google. Specific heat of aluminum. And I want you to do a percent error analysis. A percent error analysis on our experiment compared to the accepted value. Percent error. All right. It is the experimental value minus the accepted value that's an absolute value divided by the accepted value multiplied by 100. That is percent error. Okay. Percent error equals this calculation. So this is what we will determine from the experiment. You'll find the accepted values online and then do a percent error analysis. All right, that's for the second experiment. For the third experiment, the acid-base reaction, I want you to find standard enthalpy of reaction for that's the reaction that we're doing in the third experiment. This is the reaction that's occurring in our calorimeter. So you need to find a standard enthalpy of reaction for this reaction. You can find it in the back of your textbook. And then I want you to compare your value that you find in the textbook to the value that you calculate here. Now, there's a bit of a catch. This thing that you look in your text, find in your textbook, is based on 1 mole of hydrochloric acid solution reacting with 1 mole of sodium hydroxide solution to produce 1 mole of sodium chloride aqueous and 1 mole of water. And that's not what we're doing in this experiment. Okay? We're not using 1 mole of each one of those. So you need to make an adjustment accordingly. You need to make an adjustment accordingly. And then I want you to do a percent error analysis on those two values as well. Again, what you find in your textbook will be based on 1 mole of each one of these. And we didn't use 1 mole of HClAq. You have to find out how many moles we did use and make the adjustment accordingly. How many moles of sodium hydroxide did we use? Make the adjustment accordingly. How many moles of sodium chloride were produced? How many moles of water? Because we're not going to use 1 mole. A little bit, substantially less, actually. But you have to make that adjustment accordingly. The value that you find down here, all right, has to be adjusted to compare to the value that you find up here. in your textbook. And that's all I'm going to tell you about that. If you have issues, you can send me an email or we can set up a Zoom session. But I'm asking you guys to do a little bit of research and try to find the answers and how to do that yourselves. But don't hesitate to contact me if you're having issues.